Good morning, everybody. This is Ben Keyser with Applied Flow Technology, and I want to thank you all for attending our AFT Fathom Introduction webinar today. And I'm really excited to present the material to you all. And in case you're all wondering, when you see the date on my computer, it's February 8th, where the webinar was scheduled for February 7th. Well, I did the webinar on February 7th and I forgot to hit the record button. So I apologize for that. And so I am re recording the webinar content for you all. That way, for any of those of you who were able to attend yesterday, you'll be able to still have the recording. You can pass it on to your colleagues. And then for those of you who weren't able to attend yesterday, you'll see the same content, but with a February 8th date in my computer. So, anyway, with that, I'm going to go ahead and get started. And the slides are incredibly brief today. And I wanted to highlight that AFT offers a very wide range of products that can offer you a full solution for your piping systems when it comes to pipe flow calculations. And so we've got AFT Fathom for liquid systems, AFT Arrow for gas systems, and AFT Impulse does Water Hammer for liquid systems. I'm not going to spend very much time going into the details of each of those. Rather, I want to point out a few things on our website. One is if you go to AFT.com, under the products menu, you can go to the AFT software overview, and this is where you can find an overview of all of our different products. And if you click on any of them, it'll take you to that specific product page. I highly encourage you all to take a look into the add-on modules for each product that are available. They're very useful tools that will extend the advanced modeling capabilities of our software for you, and I recommend checking those out. You can also read about our system requirements. You can access pricing if you're within the United States. And so a lot of useful stuff. You can access demos, latest releases, etc. That's the first thing I wanted to point out on our website. The next thing I wanted to talk about is when you're using our software, how do you know if the results are correct? Well, there's two ways. One is AFT has done its own quality assurance with building several models of various published resources that are available from tech papers and textbooks and handbooks and whatnot. So if you installed the software on your computer and you drilled down to the AFT application folder, went into verification, this is where you can find our verification help file, and it talks about the results comparison between the Fathom model that we built of the published example and then the results of the published example reports. And we compared the two, and that's an excellent way that you will be able to see how Fathom is calculating the correct results properly. And so there's a ton of them for Fathom. There's several for Arrow and Impulse as well. And so it talks about the verification methodology that we go through. And then you can look at the comparison of results for each of these. And you can view the model in the help file. This is what the model would look like. And then if you open up the model directly, you can open up the model and see how it was run. So that's one way that you know that you're going to get the right answers. The other way is if you go back to our website, and then under the services menu, you go to nuclear validation. This talks about the full-on nuclear verification and validation that Archon Engineering did for each of our software products. And it's a very extensive verification process, and it allows our software to be used in safety-related systems in the nuclear industry. And so this is a whole additional significant layer on top of what we've already done for quality assurance. That way you can ensure that you're getting the right results. And if you're interested if you are in the nuclear industry and you're interested in their commercial grade dedication package, you can click on this link right here, and that'll take you to Archon Engineering's website. The third thing I want to point out is under our Learning Center, we've got a lot of resources that are really useful for you. We've got training seminars, case studies, tech papers, video tutorials, tips and tricks articles, etc. If you go to the case studies area, this is where you can find all the different case studies that various users have done with our software for their specific industrial applications. And they're excellent studies, and we've got over 40 of them. And so if you use these filters, maybe you want to focus in on the Fathom case studies for the oil and gas industry. That makes it really quick and easy to find the case studies that you might be interested in. So that's our case studies page. And finally, as you all, I'm sure, you've found how to find our webinars that we're doing. Again, if you go to Learning Center, webinars, and then upcoming webinars, this is where you can find all of our scheduled webinars that we'll be doing. And then if you go to the webinars tab again, you can access previously done webinars on our webinar library. So check back often. You're always going to be finding new content here. Really, really useful. Okay, here's what we're going to do today. I'm going to build this example of a water delivery system, and I know that it's probably not indicative of the system that you deal with on a daily basis, but you're going to get a really good feel for the overall model building and model definition process. And so that'll it'll show you how easy it is to do this. And so even for you seasoned users out there that are listening in, you're going to certainly pick up some good tips and tricks that will help you be more efficient. So here's what the example is going to be. We need to pump 500 gallons per minute of water up a hill over a 200-foot elevation change. And so there are several things that we don't know. We don't know the pipe size. And so what we're going to do is we're going to start off by guessing a pipe size for the entire system, and we're going to change that pipe size. We need to change the pipe size in order to ensure that our velocities are under 6 feet per second. So that's our first requirement, is velocities have to be under 6 feet per second there. The next thing is that we do not know what the liquid supply tank height is, and that's this guy right here. So we need to figure out what supply tank liquid height that we need in order to ensure a 2 psig suction pressure at the pump. So we want to make sure that we have plenty of suction pressure available and lots of MPSH for our pump, just to avoid any potential cavitation problems. So that's the second requirement that we have, is we need to figure out what liquid height we need in order to get 2 psig at the pump. Thirdly, the last thing that we don't know is we don't know what the pump curve is. And so we're going to do a pipe sizing calculation. We're going to do essentially a tank sizing calculation. And of course, we're going to do a pump sizing calculation. And we're going to find a pump curve that will fit the operating point of 500 gallons per minute and meet all the system conditions. And once we find a pump curve, I'm going to show you how you can easily generate a pump and system curve. And then if there's time, I might be able to show quickly how you can add on a system expansion. So we would need to figure out how many pumps we need for a higher flow requirement that we might have. So I've already started Fathom. What do I do now? And so at this point, I'm going to jump into the software and move my PowerPoint out of the way. So this is AFT Fathom. And if you're not familiar with our software, I'm going to give you a really quick tour here. This whole blank white space that you see right here is our workspace. This is our canvas where you're going to build a model of your piping system. And in order to build a model of your piping system, you're going to use the components in the toolbox here on the left-hand side. And so all of those components will influence the pressure and flow and perhaps temperature behavior of your piping system. And I want to highlight that we use a general term for components called junctions. So whenever we use the word junction, it could apply to any of those components in this toolbox here. And a junction is anything that's not a pipe or an annotation note. Next, what you would do after you finish drawing all your junctions on the workspace is you would simply play connect the dots with the pipe drawing tool right here. Also, when you're building a model, you got to have boundary conditions for the software. And so there are some common boundary conditions that you'll use. There's a reservoir junction, an assigned pressure junction, and an assigned flow junction. So if you're trying to model a physical tank, or maybe your supply or discharge is a large lake or pond perhaps, then you would use the reservoir window here where you would define a few things. You would specify the liquid surface pressure, the liquid surface elevation, and the elevation or depth of where your pipes are connected in that tank. So this is one particular type of boundary condition that you'll use. The other type of boundary condition could be an assigned pressure junction. And so for an assigned pressure junction, this is where if you know what the pressure is exactly at a particular boundary, you'll simply enter that pressure directly as well as the elevation. And that's all you need for an assigned pressure junction there. A question you might have is, what would you do if you have a pipe that is discharging into the atmosphere? You're just discharging right out the end of a hose. Well, the thing about the pipe component or the pipe tool is that you have to have a junction on each end. So if you are discharging into the atmosphere in that type of situation, here's what you would do. You can put the assigned pressure junction on the end of your pipe and then simply define atmospheric pressure for that assigned pressure junction. Next, if you want to calculate the pressure drop in the pipe and you know what the flow rate is, then you can use an assigned flow junction on the inlet. And for the assigned flow junction, that's where you define your known flow rate on a volumetric or mass flow rate basis. And then you can choose these options depending on if it's a supply boundary or a discharge boundary condition. And so that's how you would use the assigned flow junction as a boundary perhaps. All right, let me go ahead and clear these guys out of here. The next thing that you want to do is when you're not sure where to start with the model building process, focus in on the status light down here in the bottom right-hand corner. Red means stop and green means go. And so if you go down and you click on that red status light, it's going to bring up a checklist of items that need to be completed before you can run your model. So let's just go through these together one by one. The very first item is to specify solution control. This is the tolerances that will dictate if you have a converged solution or not. AFT Fathom uses tight, robust tolerances that are really good, and they will solve about 90% of the cases for you. So more often than not, you're not going to have to go into this window and mess around with the solution control. What is already defined is just fine. And so that's why that is already a green check mark, because that's already done for you. The next thing is to specify your system properties. This is where you define your fluid information. Now, you've seen it a little bit, but I've not pointed it out yet. Wherever you see this blue highlighting, that indicates required input. So when you're defining a fluid, if you choose the most simple option for a user-specified fluid, the minimal required input that you need is simply density and dynamic viscosity. That's all you need to be able to run your model and get solution for your results. So you can also change the units that you're using with these drop-down menus, and that's all that you would need to specify. You can also specify a vapor pressure if you want to know if you're cavitating anywhere in your system. Fathom will identify where that's happening, and then also it allows you to compare your, or it allows you to carry out MPSHA calculations for your pumps. Next, I'm going to go to our next fluid modeling option, which is AFT Standard. We've built in about probably 50 different fluids into AFT Fathom that you can work with. And all of these fluids here are functions of temperature. You would simply define a temperature right there. You can change the units, calculate your properties, and bam. These are the properties that are going to be used in every pipe throughout your system if you are using the constant fluid properties option. Let's talk about what variable fluid properties means. So if you were to choose the variable fluid properties option, this would be a situation if you have two different fluid streams coming together where you've got fluid A in this pipe and then you have fluid B in this pipe, and then they mix together. The variable fluid property option allows you to individually define what the fluid properties are in each individual pipe. And so when you choose the variable fluid property option, this is an application where you would do that. Next, we've got a couple of heat transfer options available for you. One of them is just a simple heat transfer option with a single fluid. And so this is the more common heat transfer option that you will use. It allows you to do various heat transfer calculations like convection in pipes. You can account for radiation or heat tracing as a constant heat flux. You can model layers of insulation either inside the pipe or outside the pipe. You can do lots of heat transfer calculations with heat exchangers. You can even do heat transfer with pumps, where the pumps will add heat to your system fluid due to their inefficiencies. One thing I want to mention with regard to heat transfer is if you have two different temperature streams mixing together, we will actually calculate what the mixture temperature is for you by doing an energy balance around that mixture point. And so that's a big distinction between AFT Fathom and some other software products out there that you would find is other products, you would have to figure out what the mixture temperature is ahead of time. We do it for you. So the heat transfer capabilities are very useful. The second heat transfer option with multiple fluids, this allows you to model both sides of a heat exchanger within the same model. So let's say that you have a heat exchanger right here, and that's the tube side, and then you have another heat exchanger right here, and that's the shell side. Well, you've got your one fluid loop on the left, and then another fluid loop here on the right, and that kind of looks like two people talking to each other. And so the multiple fluids option is where if both sides of the heat exchanger are fully liquid phase, and same thing for their loops, you can thermally link together these two heat exchangers, which would model the same physical heat exchanger in the same model, and then you'd be able to model the respective loops in the same model itself. And so, maybe this is a cooling water loop, and maybe this is a hot oil loop. That's what the multiple fluids option would do for you. All right. Moving right along here, if you want more accurate water data, you can use data from the ASME steam tables. And then Chempack is incredibly useful. Chempack is an add-on product that can be used with all of our software tools, Fathom, Arrow, Impulse, etc. And it allows you to do very accurate thermophysical property calculations. And not only are they very accurate, but the fluids in the Chempack database also knows where the saturation lines are. So if you're doing the heat transfer option and your temperatures are getting too high throughout your model, then Fathom will clearly warn you that you've got vaporization in your line because the temperatures are too high and your fluids are boiling off. So that's a really powerful feature of Chempack. The other thing that's useful is you can do Chempack mixtures. So again, Chempack has about 600 or 700 different fluids that you can work with. And so if you want to define a multi-component mixture, all you need to do is just select a fluid, specify what the mass or mole fraction is, and then add it to the list, and that's how you'd be able to define your mixture. Once you define your mixture, then the thermophysical properties of that mixture will be calculated for you. And that's a really powerful thing because that's really hard to do by hand on your own. So if you've not done so already, definitely check out using the Chempact database. All right, there are some different viscosity models that are available to you. You can do different paper stock models, power law, Bingham plastics. If you do a power law or Bingham plastic, you can enter rheological data for your shear rate versus shear stress, and that will calculate the constants for you. So those are some non-Newtonian fluid modeling options that you can work with. And then last but not least, on the system data tab, this is where you can define what your local atmospheric pressure is. You can define what your transitional Reynolds numbers are, and that's basically all there is to it for the system data tab. All right, so in my model, I'm going to use AFT standard water, 1 atmosphere. Temperature is going to be 70 degrees Fahrenheit. Calculate properties and click OK. And now you can see I've got a green check mark. My fluid values are fully defined now. Next thing is to define all pipes and junctions. In order to define all pipes and junctions, there has to be pipes and junctions. So I'm going to do a couple things first. I'm going to turn on my grid. That will be a little bit easier to build my system. Next is I'm going to change my font size. So I'm going to make my font sizes nice and large and easy to see. So I'm going to do large font size. I'm going to make my icons larger than they usually are. Same thing with my pipes. That way everything's nice and easy to see on the workspace, especially when I zoom out like this to fit more things on the model. So I'm going to just start building a model by dragging and dropping out these junctions onto the workspace. So there's a supply reservoir, and then I've got a screen or a filter followed by a pump. We got a control valve. We got a couple of elbows. After you draw one thing, you can click on Control D on your keyboard for duplicate, and that will draw another one on there for you. Simply copy and paste in one. And I've got a valve, and then another elbow, followed by a discharge reservoir. There we go. All right, so there's my system. Now that I've laid out my components, the next thing to do is to essentially connect the dots. So I'm just going to double click on the pipe drawing tool and pretty much go from the middle of one junction to the middle of the next. And I did miss one of them, so I'm going to have to go back. I missed that too. So I just need to click that guy and get that in the middle there, and then move this to the middle. There we go. All right, so now my whole system is fully drawn, and I'm ready to begin the model definition process. But before that, I want to move my labels around. That way they're not being covered up by the pipes. And then you can also rotate your icons. That way they appear to flow into the pipes properly. It makes no difference on the results, but it's really nice for visual aesthetics. This elbow here, I'm going to right click. This is going to be a miter elbow. So I'm going to change that icon with the way that it looks. There we go. All right, perfect. Everything is set and ready to be defined. So if I click on define all pipes and junctions, it does two things for me. One thing is that it turns on the light bulb here, and this will highlight any label for a junction or a pipe in red, which is a really good visual indicator for any component that might be missing some information. So if you got a model of hundreds or thousands of pipes and junctions, and it won't run because you're missing information, this is a great way to figure out where you need to define some input. Second thing that it does is it pulls out our list undefined objects window. This gives you a summary of all the pipes that are undefined and all the junctions that are undefined. If you click on any of those, what it will do is it will tell you which information is missing. So that's really useful, because if you're just learning the software for the first time and you don't know what input you need, this will tell you. Also, it'll select that component on the workspace and it'll move the model to that location so you can easily find it. So again, if you're trying to navigate a large model with thousands of pipes and junctions and the model won't run because it's missing input, use this feature right here and I'll take you right to that area where you're missing some details, and you can define it, run your model, and move on with your life. Okay, so I'm going to start off by defining the pipes first. So if I open up a pipe here, in order to find the input, you can either double click on a pipe or junction or select it on the workspace and hit enter. So this brings up our pipe property window, and as you can see with the blue highlighting, the minimal required input is inner diameter, length, and friction model. That's all you need in order to fully specify a pipe. If you go to the friction model area and you choose user specified and you click on the drop down menu, you can do any of these different friction models: absolute roughness, relative roughness, Hazen-Williams, explicit friction factor, etc. So you have access to all of those when you do a user specified option. The other way of defining your pipe is to choose from the pipe material database. We have built in a pipe material database that contains probably, looks like 12 to 15 different pipe materials that you can work with. When you select any of these, you can then choose from a drop-down menu of nominal sizes and schedules, and there, that will quickly define your pipe for you. So that's the other way that you can do it without defining what the inner diameter is directly. Now, I'm sure a lot of you are asking, well, there's a pipe material in my system I need to model, but it's not in your list. Well, it's very easy to create your own custom pipe material database. And once you create your own custom pipe material, it will appear in this list, and that's very easy to do. That's outside the scope of this webinar. If you go to our website, aft.com, and you find our blog page for our tips and tricks articles, and you go back a few pages here to tips and tricks, I've written 4 different blog articles over time on how to deal with databases. So if you go to page 4 or simply search for the word databases, you'll find them. So databases, there it is. So I wrote 4 different blogs on databases. I introduced them, and then how do you do custom fluid databases, custom pipe materials, and this is how you can actually share those databases of custom information with other people. So read those blogs, and that'll get you well up to speed with how to deal with databases. Now, I don't want to go through and define every single pipe one by one like this. And so because I don't know what the diameter of the piping needs to be yet, I'm going to start off with a guess of 4-inch, but I'm going to do some global editing because all pipes are going to be the same material, size, and type in this system. So what I'm going to do is I'm going to go to Edit and then Global Pipe Edit, and I'm going to click on All, because all pipes are going to be steel material. They're going to start off as 4 inches in diameter, and I'm going to set the nominal size on the workspace. Now, here's the thing. You see this length is highlighted. That indicates that I have to define it, but I don't want to define the length right now. Well, the thing is, you don't have to, because when you're doing a global editing operation, this pipe property window here is only a template window. So you only need to edit what you actually care about modifying. You can leave the other stuff alone. So in this case, I only care about material, size, type, and friction model. I don't have to define the length right now. So when I go in and I click OK to accept these changes, it pulls up a list of parameters that I want to change. And so I click All and then Apply Selections. So now you can see all my pipes are 4 inches in diameter. Now I'm going to go back and I'm going to do the pipe lengths separately. These 4 pipes right here are 20 feet long. So if I select them on the workspace and then go back into my global editing window, you'll see that they're already checked off for me. So that saves you some time so you don't have to go through and manually check those boxes. So they're going to be 20 feet long. This is where global editing is very powerful, but you have to be very careful because you don't want to just willy-nilly click the All button. You have to pay attention to only check the boxes for the specific parameters that you want to change. So here I only care about changing the length now. So that's the only box in that list that I'm going to check. So I'm going to go in, check the box for length, and apply the selections. Next, I know that pipes 6 and 7, those guys are 100 feet long. So we type in 100 feet, check the box for length, and apply the selections. Got 2 more pipes. This pipe right here is going to be 30 feet long. And then last but not least, this pipe is 1,000 feet long. Now, I want to point out a couple of things because this is a really long pipe. And this pipe here, in reality, is not going to be simply traveling linear from point A to point B. It's traveling all over the place. And so you've got a whole bunch of fittings in this pipe that you still want to account for, but you don't want to have to actually model them with all these separate junctions because that's just going to clutter up your model. They're only minor losses, and you have to put in a whole bunch of extra short pipes. So in order to account for those minor losses without having to actually draw them on the workspace is to go to the Fittings and Losses tab and click on this button right here. And this is where you can simply go to each of these different fittings, simply put in a quantity for how many you have. You know, maybe you've got 5 of those and, 3 of these. Maybe you've got some valves in there. You got 2 of those, 3 of those. And so as you can see, whenever you click on any of these rows, it's going to pull up a picture of what that loss model looks like. If you double click on the picture, it's going to tell you the reference that we're using for that loss model. Now, as you go through and you define the quantity of how many of these there are in your system, you go back to the summary and it's going to have a really handy summary table for you. So this is a summary of all the fittings that you're going to lump into the pipe. It simply totals up this K factor, and it's going to lump in that K factor as an additional frictional loss to your pipe. And so this is an excellent way to be able to still count for all of your minor losses in your system in a very easy fashion without having to model them as actual junctions. And here I'm going to throw on an additional K factor of 15. That way, just in case if I missed something, we've got some additional losses there that we're counting for. Next, how do the pipes pick up the elevation change? Well, the way that the pipes pick up the elevation change is that you have to specify elevations for every single junction throughout the model. That's the minimum thing for junctions that you have to specify is elevation data. And when you specify the elevations in the junctions, that's how your pipes pick up the elevation changes. That being said, if you have a really long pipe that's, doing something like this, it's traveling all over the place, well, you could model this in reality by putting branch junctions all throughout this area. This is the branch junction right here, and that's simply a connector point for pipes. And so you can put a branch junction at each of those locations simply to get the elevation change of your model. However, it's going to be gruesome and take a long time to do. And again, you've got all these extra short pipes, and you don't want to deal with doing that. There's an easier way. So if you go to the optional tab, you can click on Use Intermediate Pipe Elevations, specify how many there are, and this is where you can track the point-to-point length versus the end elevation. So if your pipe is moving all over the place, this is how you can track those intermediate pipe elevations very easily. When you run your model and get results, if you did a graph of the pressure in that pipe, you would see how the pressure changes as the elevation changes throughout that pipe. So this is what you would do when you don't want to have to put on all those extra junctions in there. If you have this data in a spreadsheet, you can easily copy and paste it in, or you can import it from a text file. Maybe you have some GIS data that you want to import as the elevation changes. And if you can get that into a CSV file, you can just import it right in. And so very easy to do. In my case, I'm just going to let the pipe travel linearly from A to B. Okay, now we're done defining the pipe, so we're going to go through and do the junctions. So I'm just going to go from left to right here. My supply reservoir, I don't know what the liquid height is going to be, so I'm going to guess at 10 feet, and that value is going to change later. And I'm going to put my pipe connected at the bottom of that tank there. Next is I've got my filter. It's going to be at a 0-foot elevation. We've got a few standard screen models that you can work with. I'm going to do user-specified resistance curve. Because my manufacturer of this filter told me that my design flow rate of 500 gallons per minute, I'm going to have a 5 psi pressure loss. So if I enter this data point and generate a curve, this is going to give me a very bad resistance curve. That's not correct because it represents the same pressure loss at all flow rates. That's not realistic. Also, if your real system flow is really low down here, this would represent an infinite resistance, and that very well could, well, A, it's going to lead to incorrect results. B, it could potentially cause convergence difficulties. So what do you do when you are in the absence of any other information other than a single data point? Click on this button, fill as quadratic. It includes the origin for you, which whenever you're defining curve data, you should always include a data point at the origin. And then the third data point will be extrapolated along a quadratic. So when you're only given one data point and no other information, this is going to give you a much more realistic pressure loss characteristic for that type of component. So that's how you would correctly define a resistance curve. Next is I'm going to do my pump. And for your pump, you could enter a pump curve, but I don't know my pump curve yet. I need to size my pump. So in order to do that, I'm going to use a fixed volumetric flow rate. I want 500 gallons per minute. I'm shooting for 75% efficiency. And that's all there is to it for the pump. For my valve, I'm going to do a constant pressure drop valve of 5 psi. And so this is just a this is a placeholder. Maybe I do want to put a real control valve there. I'm not sure. This is a situation where you know very little about your system. You don't know your pipe sizes. You don't know your supply tank heights. You don't know your pump curve. Is there actually a control valve there? Maybe, maybe not. So this is really just serving as a placeholder for me right now. And I want to make sure that if I did have a real control valve, I want to be able to maintain at least a minimum pressure drop of 5 psi at my desired flow rate. That way, whatever control valve I might select, it would be able to have good controllability for its lifetime. And so that's how I'm going to model my control valve right now. Next is my elbows. So this is going to be a standard elbow. The K factor is picked up from the loss model based upon the upstream and downstream pipe diameters. My second elbow is also going to be a standard elbow, but this is going to be at a 30-foot elevation. And I've got a valve. And you can define a valve in different ways. You can do a CV or a K factor or a resistance curve. For the CV option, if you went to the optional tab and you defined a open percent versus CV curve, well, A, in the results you can see what the actual open percent is. B, if you go back to the loss model tab here, you can click on this option, and that way, if you don't know what the CV is, but you know your open percentage, you can specify your open percentage directly in that case. Here, I'm just going to use handbook data. I'm going to use the very top option. That's going to give me a K factor of about 2.5. Next is this is going to be a miter elbow, and it's going to be at a 45-degree angle. And last but not least is my discharge reservoir. This guy is at a 200-foot liquid surface elevation, and that's where my pipe is going to be connected. Perfect. So now, as you can see, you've got all green check marks. You have a green status light. You could run your model and get results right now if you wanted to, But before I do that, I want to do a few things here. What I want to do first is look at the model data window. The model data window is an excellent tabular format for all of your input information. You've got a general section at the top. If you put in notes for pipes and junctions and scenarios, you'll see all the summary of all the notes right there. You've got your piping information in the middle, and then your junction information at the bottom, where each junction is on a different tab. And so those are the three different sections. I'm not showing every single possible input piece of information I could show. If I went right here to the model data control button, this is where you can dictate which input parameters are shown or not shown. So these are all the parameters for your pipes that are available, and these are all the parameters available for this type of junction. So if you do your junction parameters, you've got to click on the drop-down menu right here, choose a junction type, then specify which parameters are going to be shown. And so that's how you can display different types of parameters. Then, once you get your model data window formatted with the different input parameters that you want to have shown, you can easily print this out as a really nice looking PDF, and that way you can include the model data window with your report, and you'll have a full input report for your system when you're doing your project. If you click on fittings and losses, you'll see here that it contains a summary of the fittings that I have included in that pipe. If you go to pipe detail summary and go all the way down, you'll see every single pipe fitting and loss detailed explicitly. And so you can also print out the pipe detail summary, and that'll contain all of your detail right there for you. So that's the model data window. That's the first thing you want to do, is scan it for a sanity check. Make sure your units are consistent. You're not having, huge orders of magnitude unit errors and things like that. And I use the model data window all the time for troubleshooting, so it's a really good thing to get familiar with. Next is our inspection feature. If you want to quickly see what's the input information for a pipe or junction, simply right-click on that pipe or junction and hold. So if I right-click, you can see here what the input information is. Same thing for junctions. Then if you click on the Properties tab here in the Quick Access panel, and you select any of those, it'll display the input information for you right up here, just like the way that it did before. If you had output results, it would also display the output information on either way of inspecting your input. Okay, a couple more things that I'm going to do before I run my model. The next thing I'm going to do here is I'm going to take this system, I'm going to duplicate it, because I need to figure out what pipe size I need. So I'm going to do a duplicate special, and I'm going to put this guy right there. Move him around a little bit. There we go. And then I'm going to duplicate it one more time. I'm offsetting the pipe and junction numbers by 100. This makes it really easy to see that pipe number 1 corresponds with pipe 101 and pipe 201. I'm a bit too far zoomed out, so I'm going to move these just a little bit closer together. That way, when I zoom out, I can actually see my icons. Dang it, I keep accidentally moving that off. There we go. Okay. Perfect. So here's why I did this. Again, you can see pipe 1 corresponds with pipe 101 and pipe 201. So the piping system in the middle right here, let me reselect it again. This is going to be a 5-inch diameter piping system. So I simply go in, I can do a global edit. They're already selected for me. I just need to make the change once, and that sets all those pipes to be 5 inches in diameter. And then this system at the bottom is going to be 6 inches in diameter. So I go in and I change it to 6 inches, click OK, 6 inches, apply selections, perfect. So now I've got 3 different systems that are identical except for the pipe size, and they are able to run simultaneously on the same workspace. There's no limit to the number of individual piping systems that you can run on the same workspace at the same time. You can do as many as you want. So next thing I want to do is I want to make sure that my all my pipes are staying within that 6 feet per second threshold for velocity. So in order to do that, I'm going to use the Design Alert Manager right here to make sure that I'm maintaining code compliance. So this is going to be 6 feet per second max velocity. You can apply, you can do design alerts for junctions. So maybe you have a minimum pump discharge pressure. You can do a design alert for that. I'm going to choose velocity here, and it's going to be 6 feet per second. Add it to the list. I'm going to apply it to all my pipes. The reason why this is useful is because when I go in and I run my model, it's going to tell me which pipes are not meeting that criteria very clearly. So you can do as many design alerts as you want, not just one at a time. You can do design alerts for velocity and maximum and minimum pressures, perhaps, anything that you'd like to do. Okay, next thing I want to do is I'm going to set up my goal seeking control module so I can figure out what my tank heights need to be. Imagine, if you will, if I had to run this model and individually change each of these supply tanks by themselves and constantly go through a guess and check process to ensure that the suction pressure at each of these pumps for each of the system equaled 2 psig. So that would take a lot of time, because it's really easy to do that when you're just dealing with one input that you're changing one at a time. But if you're trying to change multiple things at a time, it's a lot harder to do that manually. So don't do it that way. Let goal seeking control do it for you. So what might take me 10 to 15 minutes, GSC will do in 2 seconds. So let me show you how to do that. I'm going to go to the Tools menu and then click on Activate Modules, and I'm going to turn on Goal Seeking Control. And then I'm going to go into my Goal Seeking Control Manager. I'm going to define a variable. So my variable is going to be the reservoir liquid heights. Then once I do one, I can select that row and I can duplicate the variable. All I need to do is change the number. Saves me a lot of time. Next, I go through and define my goals. And so my goal is going to be based upon pressure, has to equal 2 psig at the outlet of pipe 2. The location of that is right here, right at the pump suction. Now that I've done that goal, I'm going to select it. I'm going to duplicate the goal twice. And so here, again, all I need to do is just change the number. Saves me a lot of time. So now wherever you see a V, that means that there's a variable on that object. Wherever you see a G, there's a goal on that object. All right. I'm ready to run my model. I'm going to customize my output just a little bit. And so I'm going to go into my output control window here. And there's some parameters I don't care about, so I'm going to remove those parameters that I don't want to see. And then I want to add my nominal size all the way to the top. And then velocity, I'm going to change all my pressures to psig. There we go. Next, the thing I've not mentioned yet is that our software supports docking and dual monitor usage. So if you want to pull your model data window off into its own separate monitor, that way you can look at your model and your input at the same time, you can. Or you can dock them to the side. So I can put my output, my graph results, and my visual report on the right side, and then my model data and my workspace on the left. So now that I've got my system built, I'm going to hide my quick access panel. There we go. Okay, that's a little bit better. So now I have my input windows on the left, my output primary windows on the right. Erase all the drawings. Okay, going to run the model and let's see what we get. Pump and pipe sizing. Look at that, less than a second, and it already figured out what liquid heights I need. So let's take a look at that. GSC variables. As you can see here, this tells me what the resulting liquid heights need to be for each reservoir. If you pay attention to what's going on, this is variable number 3. This is for my 6-inch diameter piping system. So when you have a larger diameter pipe, you don't need to have as high of a liquid level. So you don't have to have as large of a tank perhaps. So that's a good visual indicator that I'm going to go with the 6-inch system. Next thing is we now know what liquid heights we need, but are our goals being met? Well, they are. I defined a 2 PSIG goal, and you can see that it's been met here. How can I confirm this? Well, if you go back to the workspace and we zoom in, I can right-click on that pipe and look at that. 2 PSIG for the suction pressure. And then same thing with this pipe, 2 PSIG. And then right here, 2 PSIG. So that's good. That shows me that my results are met. Now let's take a step back and look at the warnings here. The warnings are telling me that I've got all these design alerts that are being violated. What that means is I've got velocities that are higher than 6 feet per second, and when you look in the results window here, it's actually going to highlight those violations for you. So this just shows me that my 4-inch and 5-inch diameter piping systems are not going to cut it. I need to go with the 6-inch diameter system. So I'm going to create a child scenario, and I'm going to size my pump now based upon the 6-inch diameter system. And so I'm going to go to the scenario manager, and I'm going to call it pump curve. The scenario manager is one of the most powerful tools of our software because it allows you to model any type of operating case within the same model file. So you can change any parameter in any scenario that you want. There's no limit. You can turn things on and off. You can change boundary conditions. You can change control valve set points. You can change pump curves, pipe diameters, pipe lengths. You can have completely different systems in different scenarios that don't even relate to each other, and you can still make that work. And there's intelligence built in such that if you make a change in the parent scenario and the child scenario has not yet changed, those changes will pass down to the child scenario. And so think of this scenario manager like a family tree. You know, you have a whole family tree with, you know, several parents, and then each parent has several children scenarios. Well, make the change once at a parent, and all the children are going to get those same changes. So this is where the scenario manager is extremely helpful. Make sure that when you get into using our software, get very familiar with the scenario manager. It'll help you out a lot. So here in my pump curve scenario, what I'm going to do is I'm going to take the results of the pipe liquid height variables for the tanks. I'm going to transfer them now as input. So now, if I go in and I right-click on any of these reservoirs, you can see that you've got the real reservoir liquid height that you need, 17.3 feet. Next, since I know that my 4-inch and 5-inch diameter piping systems are not going to cut it, I'm just going to delete those from the workspace. They're still in there in the base scenario, but they're not in there in my pump curve scenario anymore, so I'm only focusing on this single system. Next, I'm going to disable my GSC to speed up my runtime here. That way I don't have to have it running. And I'm going to run my model. And so now I'm going to size my pump. So these are the same results that you saw before. And to size your pump, I'm going to click on this button right here. And I'm going to go to the internet to find a vendor that will have a pump that will meet that operating condition for me. So I'm going to use Berkeley Pumps. IntelliClip works with over 30 different pump vendors. So if you subscribe to different vendors, then you can add them to this list. These ones that are being shown, they display their online pump catalogs for free without needing a pump subscription. So if you've got your own, you can add them to this list here. So I open up a browser and I go through the very quick pump selection process. I'm going to choose the top one right here. And then I'm going to choose the second row because that's a pump where my design floor is operating very close to the BEP. You can download all of that spec sheet information as a PDF if you want, but what you need is this IQX file. And I'm going to put that in my desktop so it's easy for me to find. So now, when I go back into Fathom, I move on to step number 2 right here to open up that file. So I'm going to now apply that pump data to my pump. So now when I open up this pump here, there it is. I've got my head curve, my MPSH curve, efficiency. If you open up the enter curve data button, you've got all this data here. And so this is the data that was used to build those curves for you. So it's a really quick and easy process to size your pump. As you can see, very powerful capability. When I go to rerun the model here, I want to compare it with my original fixed flow model. That way I can verify that my pump curve is doing a good job. I can compare both scenarios' results side by side with each other. So as you can see here, I've got 500 gallons per minute, 241 feet ahead, and my overall power. And then you've also got your real efficiencies, your BEP information, your MPSH information. Something I didn't point out is if you go back to the base scenario here and you compare the pump summary, you can see how the pump heads decrease dramatically with increasing pipe diameter. Same thing with the power. So, you know, the 6-inch diameter system is definitely going to save us a lot of money on those energy costs. A couple more windows that I haven't showed yet is the visual report here. The visual report is probably the most common way that you're going to display your results for your bosses and your clients. And so I'm going to customize this here a little bit and modify my text size. I'm going to make my font size 20. I'm going to add some additional digits. I'm going to do a color map because I want to map out how my pressure losses are changing throughout the system. And so now I can bring my legend down here, and there we go. I'm going to reset my panels at this point now that you've seen how you can dock your panels. And so this gives me some more real estate. This is how you can display your input or output information directly on the model itself. You can print this out on an arc size paper with a plotter perhaps. That way it's nice and big. And so the visual report is a really useful tool, you know, if you're in the final results stage or if you're just quickly running your model to see what's going on. You know, this is a great way to check your results really quickly. So that's the visual report. Graph results here is where you can do different types of graphs. And I'm going to show you how to do a pump and system curve. It says easy as going to this tab. It's saying generate. And it's already got some pre-selected data for me. So that's why I can just click generate and it does it. It's already pre-selected parameters for me. So that's good. So there's my pump and system curve. I can file this away for later. Pump and system curve. Let's do a profile plot. I want to see how is the pressure and the hydraulic grade line changing over the flow path. So here we've got pressure on the top, hydraulic grade line on the bottom. And when your parameters share a common x-axis, you can do this really cool stacked graphing where you can look at multiple parameters at the same time. Incidentally, you can also do secondary y-axes as well if you want. So I'm going to add this to the list as P and HGL versus length. Now, here's why I'm showing you the graph list managers, because this is a really powerful filing system for all your graphs. You can do as many individual graphs as you want. You can create as many graph folders as you like. Now we can organize all your different types of graphs. Here's why this is so useful, is because when you go back into the model on the workspace and you make a change, you rerun your model, you get new results, you don't need to go back in and reset all of these parameters right here. Instead of having to reset the parameters every time, simply double click on each of these graph list items and that'll regenerate those graphs lickety split for you. And so that's the graph list manager. If you want to display both graphs in the same tab, you can. Simply right click and then load both of them in the same tab. This allows you to look at both your pump and system curve and your profile plots at the same time. So there's a lot of powerful functionality there. Okay, I know that I'm just about out of time. Let me show you a couple more things with relation to pumps here. I'm going to create one more scenario, VFD. You can easily model impeller trims and VFDs. So for the impeller trims, just check that box to modify the impeller trim. You can do it as a ratio or as an actual percentage. And then for the variable speed tab, this is where you can do a fixed speed directly or a control pump set point. So maybe I don't need 500 gallons per minute, I only need 400. I can type in 400, and then what Fathom will do is it's going to adjust the pump speed in order to ensure that my flow set point is met. So when I go in and take a look at this here, in my pump summary, I've got 500 gallons per minute in my first two scenarios. In order to get 400 gallons per minute, speed has to drop by just over 6%. And that's how easy it is to model a VFD. And again, a VFD is always a better way of being able to save money rather than using a control valve. And incidentally, you can directly calculate those costs in the software. And so in AFT Fathom and AFT Arrow, you can do full cost calculations. So if you click on Calculate, you can go in here and open up your cost settings. You can enter an energy cost, maybe it's 10 cents per kilowatt hour. You can do material, installation, maintenance, or operational energy. You can do a different system life, etc. And so this is how you can actually figure out how much money are you going to be saving by using a VFD for your pump instead of using a flow control valve. You will be able to calculate those costs right away. Okay, with that, a lot of information, and I hope that you all enjoyed the webinar, and thank you very much for your time. Again, going back to our website, if you go to Learning Center and then webinars, you can access our upcoming webinars. We're doing webinars basically every first and third Wednesday of every month. So that's why we're trying to get in our webinars. So be sure to register for those. On our webinar library, if you want to see some more stuff that is really cool that you can do with pumps, fill out the form and access our webinar library. And then it's, let me find it. It's a recent webinar that I did at the end of last year. This guy right here, 10 things you can do with the pump junction. And so if you watch that webinar, it's going to show you some really cool stuff that you can do with pump modeling in AFT Fathom. So with that, I'm going to go ahead and end the webinar. If anybody has questions, feel free to either email us at sales@aft.com, or if you have tech support questions, you can email support@aft.com. You can also call us at our phone number right here below. So whenever you want to contact us, we're happy to help and look forward to communicating with you all. Thank you again very much for your time, everybody. I hope that you have a wonderful rest of your day and a great week.